Okay, Chapter 7. We're going to talk about gases, liquids, and solids. And in the process, I'm going to introduce the gas laws and let's see, colligative properties. No, what causes the various phenomena we see, transitions between gases, liquids, and solids. All right. We know that we can identify either physical properties or chemical properties of substances. Physical properties, think of properties as a potential for something, as opposed to, let's see, we have properties here, and we have change here. Okay. So you can have a physical property, or you can have a chemical property, and here you can also have a physical change or a chemical change. Gonna have to get rid of that one. Another one. When you think of the difference between physical and chemical, for either one, think in terms of identity. The physical property talks about a potential for physical change. In other words, volume and shape, right? For a substance, you can change those. But at this point, we're only identifying the property. We're not changing it yet. Compressibility, thermal expansion, those are examples. Density. When we identify these, we're not actually saying anything about the identity of the substance. If we say water occupies a volume of 100 milliliters, we could easily say that ethanol occupies a volume of that same 100 milliliters. So we're not specifying what the substance is when we identify the property. Whether it has a shape, right? Can it hold its own shape? It's a solid. If it can't hold its shape but the volume is constant, then it's a liquid. And if the volume and the shape are both indefinite, then it's a gas. Density, we've done a lab for density, right? What type of property is density? Is it an extensive property or an intensive property? Does the amount of substance matter for density? No, it doesn't. Because you get more of it, you get more mass, you got more volume too. They both go up together. So when you ratio them, you get a constant value for that substance. All right, that's physical properties. Compressibility. When we talk about compressibility, and we can draw a contrast among the different phases. Are you going to take a test today? Okay. Why don't you leave those here until you get back? Take a copy of the test and go out in the hall. Otherwise, you'll hear my voice ringing in your head. So, when we look at the difference between compressibility of solids, liquids, or gases, there's a marked difference. Solids are definitely incompressible. They cannot be, the volume can't be changed by increasing pressure. At least, not as far as we're concerned. I mean, if you go to the center of a star, maybe. Or how about Jupiter? The center of Jupiter. They think at the center of Jupiter there's solid hydrogen because of the pressure. And liquids in general are incompressible unless you get very, very high pressures. We measured the volume of a given mass of water at sea level, and then go down to several miles down, like 2.5 miles down for the, where the Titanic sits. And that volume of that same mass is less for water. So water has very slight compressibility. Gases, they are compressible, no limits. Now, why is that? Well, think about the arrangement of the molecules or the atoms in a solid versus a liquid versus a gas. How far apart are they in solids? By comparison, they're not very far apart. Liquids, they're about the same distance apart, maybe just a little bit more. The only difference is in a solid, the atoms, molecules are fixed in place. They can't move. All they can do is vibrate. Liquids, they can move past one another, so there's a little bit more space involved. Gases, there is a massive amount of space between gas molecules. Compared to their size, it's as if the gas molecules don't even exist. So with all that space, when you put pressure on them, they've got room to contract. So that's why gases are compressible, solids and liquids are essentially not compressible. How about thermal expansion? What does that even mean? Well, thermal refers to heat, right? So if you apply heat to something, you expect it to expand. Right? With a change in temperature, you should see expansion. Now, it also varies with solids, liquids, and gases. In fact, different solids will expand at different rates. So will liquids. Gases tend to be more forgiving. If you increase the temperature a certain amount, then it doesn't matter what the gas is, it's going to expand a certain amount. And we'll get to that when we talk about gas laws. I remember as a kid, railroads, they had the length of the rail was like, I don't know, 20 feet or so, and then you had a gap for thermal expansion. And they just tied them together with brackets that would allow each piece to expand and contract. Now with the new types of steel that they have available for these rails, they can go several miles with no joints at all. So you don't hear any clickety-clacks anymore. That's the difference in thermal expansion. All right, I mentioned the primary differences between solids, liquids, and gases having to do with volume and shape. Definite volume, definite shape is a solid. Definite volume, indefinite shape, in other words, it has to have a container, is a liquid. And indefinite volume, indefinite shape is a gas. You have to have a complete 3D surrounding vessel for a gas. Otherwise, it'll just keep expanding until it's gone. Density. How about density? How does the density of a solid compare to a liquid compared to a gas? Solids are usually very high density. Now, if we stick to just one substance and we say in its solid phase, or in its liquid phase, or in its gaseous phase, in its solids phase, it's most dense for all but a very few solids. The solid is the most dense, liquid is less dense, and then the gas is much less dense. So for solids, we typically express their density in grams per cubic centimeter. Liquids, grams per milliliter, which is exactly the same number either way, right? Because cubic centimeter and a milliliter are identical. gases are so tenuous, we usually say grams per cubic meter because they're so, the density is so low. So, low density, moderate, medium density, high density by comparison. Now, the one notable example that doesn't follow that trend is water. When you gaseous vapor, yes, condense it into a liquid, it takes up less room, so it's more dense. But when you go from a liquid to a solid, when you go from liquid water to ice, the solid is less dense than the liquid. That's why ice floats. Now, how much less dense? About 10%. You heard the saying, 90% of an iceberg is underwater. 10% is above water. That's why they're so dangerous to ships, because you can't see how far they go out underwater. Lots of times the waves around near the top of the iceberg will beat against the side and shrink it. And underneath it'll spread out. So if you've got a deep draft vessel and you go near one of those icebergs, it could rip a hole in the side of your ship. You not even know it. Okay, I mentioned compressibility already. Thermal expansion. As a general rule, by comparison, the solid has a very low thermal expansion. The liquid of that same substance would have a greater thermal expansion, and gases have a very large thermal expansion by comparison. Okay, so how do we explain these properties? Remember, we're kind of getting this bass backwards as far as history goes, because the laws that govern these various properties were discovered first, and then the theory came after that to explain it. But the way the authors are presenting it, I got to give you the theory first. This is the kinetic molecular theory. It started with gases, explained the behavior of gases, but it was found that it was very useful to explain certain behaviors and properties, physical properties of solids and liquids. So if we look at the word, kinetic means motion. So the molecules that we're trying to describe in physical terms are in constant motion. And these tiny particles, they could be atoms, they could be molecules, they could be ions. They do have a characteristic sizes for each of these, and they don't change during any process or any description that we give them. But they are in constant motion, and each particle has kinetic energy. Okay, so, and we define the kinetic energy in these terms. All we have to know is the mass of the object and its velocity, and we can calculate kinetic energy. Now when we do that calculation, we have to use SI units, the standard units for each one. Mass is kilograms, correct? Velocity is what? Meters per second. Square that and multiply times a half. Okay, so kinetic energy would be in kilogram meters squared per second squared. Well, we give that a special unit called the joule. Okay, now these particles have kinetic energy, but we don't have the detecting power and the computing power to follow every one of the molecules in a substance. So, what we have to do is take a statistical approach. We just say that all of these molecules are in random motion, and we try to describe them in bulk. In other words, each one of the particles will have its own kinetic energy, right? And there'll be a range, right? Most of them will have this much kinetic energy, and then there'll be a few with a lot higher and a few with a lot less. So what happens when particles are in random motion? Okay. Are they just going to be independent and never see one another? It's kind of like driving in Houston or Dallas or Atlanta or some other big city. I mean, if you stay there long enough, eventually you're going to smack into somebody. Right? That's what these molecules do. They bang into each other. And when they do, they transfer their kinetic energy. Now, we assume, let me see if that's one of our, all right, the starting point for the kinetic molecular theory is that the molecules behave like billiard balls. Right? When they hit each other, they just bounce off. There's a total conservation of energy. In other words, the energy they have combined coming in is the same coming out. That's an elastic collision. But we know from that point we can modify their behavior in our minds and in calculations with respect to how they do interact. Because once they come close to each other, they will either attract or repel. These interactions are largely electrostatic. In other words, if a polar molecule bangs into another polar molecule and the positive side of the one, it bangs into the negative side of the other, they're going to attract. So it's not just going to be an elastic collision, there's going to be some energy that's absorbed by that attraction. And vice versa. If the same charges come at each other, they're going to be repelled. So by and large, as long as those interactions are not large, they won't affect the kinetics of the whole mass of particles. When they do interact, we can say that as they come close together, right, they can store up some energy in that collision. Say if they repel one another. As they attract, they're being forced together, and that's providing more of that kinetic energy is being stored in potential energy. And then they bounce away and they get that energy back. And we can make a similar argument for the attractive forces also. All right, that last statement. These, let's use the water molecule for example. Right. We talked about bond polarity already, haven't we? Yeah. Okay, so we know that this side is going to be slightly negative and this side is going to be slightly positive. So these differences in charge are permanent. They're based upon the bond itself. Right? The bond is polar in that direction. So when we add them together, we get a polar molecule. But molecules that don't have polar bonds can also exhibit momentary redistribution of their charges. Those are temporary charges, and they can also influence the attractive or repulsive interactions when two atoms or molecules approach one another. All right. The kinetic energy of these particles in each of the substances depends upon temperature. So remember when I talked about we can't track every individual particle. So one of the ways we identify their kinetic energy on the average for the substance is to measure the temperature. And the temperature is in effect an expression of the average kinetic energy of all the particles in the system. The higher the temperature, the more kinetic energy each of the particles has. I already mentioned this one. The particles essentially behave as billiard balls. Now there are conditions in which we can treat, and this is especially true for gases, we can treat the gas as ideal. That is, there are no attractions among the molecules. In other words, they do behave like billiard balls under certain conditions. Those conditions are high temperature and low pressure, which means with low pressure there are very few molecules there and they're far apart. So there are very few interactions. With high temperature, they've got so much velocity when they strike each other, those very small attractions or repulsions don't matter. They're just swamped over by the energy of the collision. So you can treat a gas as ideal if it's at a high temperature, low pressure. Now, what would that mean in practical terms? Right here, right now. This is a high temperature, low pressure. 1 atmosphere is low pressure. 25 degrees Celsius is actually, on an absolute scale, 298 Kelvin. So that's considered high temperature. Okay. Now, the differences among solids, liquids, and gases, we're going to try to explain those in terms of, well, let's see. Let me erase some of this. I don't want to erase all of it because I might need it. So let's just erase this part, and I'll talk down here. This is a way of thinking of solids, liquids, and gases to explain how they exist in their states, and with a balance between kinetic energy and potential energy. Think of kinetic energy of any particle as a disruptive force. All right, for any interaction, consider that a disruptive force. And potential energy, consider that as a cohesive force. It tends to stabilize any interactions or a group of particles in a system. Kinetic energy tends to disrupt those interactions. So, what do we see with solids? With solids, which one dominates? If we got potential energy, and also think of that as the forces drawing things together, the solid is going to have, the potential energy is going to win out. In other words, the physical state depends upon this being dominant over that one. So for solids, potential energy is greater than kinetic energy. Okay, it may look like that. And you see those little squiggly lines in there, that's meant to show vibration. Okay, I mentioned this earlier. Definite volume, definite shape for solids due to the strong cohesive forces that hold those particles together in a fixed position, and consequently a fixed volume and a fixed shape, and relatively high density, because the closer you get together, the less volume you have for the same mass. Right? If density is mass divided by volume, you decrease the volume, you increase the density. Small compressibility, right? The molecules are already close together. There's very little space between them, so they're essentially incompressible. You can't change the volume of a solid easily. Very small thermal expansion. You can increase the kinetic energy by increasing the temperature. We already said that. Temperature is a measure of the average kinetic energy of the particles. And as you add kinetic energy, you're trying to disrupt the forces holding those particles together. But at this point, they're still solid, so all they can do is vibrate. They just vibrate more. All right. For liquids, you tend to have a balance, roughly equal kinetic energy with potential energy. You've supplied enough kinetic energy, so now it's increased and this is decreased, so they're about equal. They're still packed relatively close together. They're just not fixed in space. In other words, they can do more than just vibrate. They can move past one another. That's why they need a vessel to hold them. Because if they can move past each other, they could just spread out across the table. Definite volume for our liquids, because they're still held fairly close together, but an indefinite shape. Because they can move past one another, they need a vessel. Now, okay. They still have relatively high density. Most of the time, the liquid is less dense than the solid because they need a little bit more space. But for water, it's a different situation. The solid, as the liquid turns into a solid, its crystal structure is such that it creates more space for the same mass. You've seen snowflakes, right? Catch one just long enough before it melts. Right? What shape is it?
They're all different shapes.
Okay. How many points do they have? 6. Always 6. And that's due to the way that water arranges itself in hexagons. Like that. So we can have an oxygen here, an oxygen there, an oxygen here. This is a bonded to a hydrogen. That's a weak bond there. This is a hydrogen. That's a weak bond there. And that's a hydrogen. That's a weak bond there. So the other hydrogens are out like this. That. So here's a molecule, there's a molecule, and there's a molecule. And the interaction between the positive side of the molecule and the negative side of the other molecule gives you this weak, well, it's weaker than the covalent bond, but it's a hydrogen bond. And when it forms that shape, look what happens. Instead of being close together to one another like a liquid, they go like this. They got all that empty space in between. That's why the volume of an ice cube for the same mass is less than it is for liquid water. And that gives it a lower density. But that's a special case. Most of the time, the liquid is less dense than the solid. They still have relatively small compressibility because that we haven't created a whole lot of space. Now, I suspect this solid would be more compressible than other solids because of that space. And you can see that in glaciers. Right? Glaciers, especially those left over from the ice age that were like several miles deep. The ice at the bottom of there, at the bottom of the glacier, was under enormous pressure. And it formed a unique type of solid. I don't even know the full characteristics, but I would bet that if it didn't sink in water, then it would be sit lower than ice that we form in our refrigerators. They have a relatively small thermal expansion. Most of the particle movement is vibrational, and they only move a short distance because they're packed in so tight. They're packed almost as tight as a solid, so they can't go very far before they smack into somebody else. Gases, special case here. Gases now have completely reversed. The kinetic energy far outweighs the potential energy. So the disruptive force overwhelms the cohesive force by quite a wide margin. And consequently, the attractive forces are not as effective because we've introduced so much energy into the system. And how do we do that? Usually, temperature, right? Heat them up, right? This is trying to illustrate the molecules in this gas are moving very fast, and there's lots of space between them. Notice that we're not showing any of them smacking into each other, but they're definitely hitting the walls, right? If they did not hit the walls, according to the kinetic molecular theory, then we couldn't measure any pressure. We put a device in there, they don't hit the walls, then how do you know there's anything in there? You don't. Your device can't measure it. So they hit the walls and they hit each other. Okay, so indefinite volume, indefinite shape for gases, where the attractive forces are minuscule compared to the kinetic energy or the disruptive forces. And consequently, these particles completely fill the vessel. So if we try to put a gas into a vessel that's got a hole in it, it won't be in there very long. It'll escape. They have relatively low density because they have small mass for the volume, large volume to get a measurable mass. All right, here we talk about compressibility of a gas. Since the gas is mostly empty space, gases are very highly compressible. And you can do it with just your hand. Right? You don't have to use a lot of force to compress a gas. We're just pushing the particles closer together. They have, it depends. I think it's not just moderate thermal expansion. I think they have large thermal expansion. As we increase the temperature, now we're going back to the kinetic molecular theory, kinetic. As we increase the temperature, there's more kinetic energy available. So, what are they doing? They're smacking against each other. They're smacking against the container. If the container is fixed in volume and it will not move, then the pressure builds up because you've got more energy when you're striking the walls of the container. The pressure tends to build and build and build. So, but if you have a movable plunger in there with a constant force applied to it, then as you increase the temperature, then the molecules inside are going to strike that piston with more force because of their kinetic energy. And that's going to push the piston up until you have fewer collisions on the piston, and then you find an equilibrium point. All right. Now we can talk about gas laws. I thought we were going to get more about properties. Hold on a second. Well, we did talk about properties. Physical properties. Maybe we're not going to talk about chemical. Yeah. I guess we'll have to leave the discussion of chemical properties and the changes for later. We are going to do a lab detecting signs of chemical change. That's next week. So maybe that's how we're getting it in there. We're doing a lab.
The lab we did last week's not due till next week, right?
Correct. Okay. Yeah, this will work quicker. And I'll just clean up the ghosts with my rag. If there are any ghosts. Not too bad, actually. Okay. Gas laws. Remember at the very beginning of the semester, close to the beginning, we talked about the difference between a law and a theory. All right, what does a law do? It just explains what happens. Right? Under these conditions, this will always happen. That's a law. A theory goes further. It says, under these conditions, this will happen because. And that's why, and that's where the kinetic molecular theory comes in. We know the gases are going to behave this certain way, and that theory explains why they do it. So we got gas laws that are going to depend upon these four variables, right? Pressure, volume, temperature, and the number of particles. That's my abbreviation for moles. We talked about moles yet? I think so. Moles, okay. Yeah, I'll take care of it later. Let's see. So, in order to describe the physical properties and the physical changes that can take place for any gas, we need to nail down these four variables. Okay. We measure pressure, we can measure volume, we can measure temperature, and we can tell how much of it is in that space. Well, if you want to see what effect one has on the other, you need to hold two of them constant. So if we wanted to say, how does pressure affect volume of a gas? In that case, the temperature and the number of moles must be constant. Or if you want to say volume changes with temperature, then you've got to hold the pressure and the moles constant. Okay, and that's what these laws are going to do. But first we need a unit of measure, a way to measure pressure for a gas. So we're going to start with this one. How do we measure pressure? Well, pressure by definition, under any circumstances, is a force per unit area. So does that make it extensive or intensive property? Intensive. Think, whenever you see a ratio of two variables, think intensive. There are a few that are intensive properties that are not ratios, right? One of them we talked about already, temperature. Okay, so that's the physical definition of pressure, but how we measure it is another issue. And let me see. I don't want to steal my own thunder. or diverge too far. Okay, we are going to do it. Historically speaking, how was the measure of pressure developed? And I'm going to come back to that slide because I want to go to, I forgot to synchronize my slide, I don't know if it's going to work now, but I'll do it anyway. I'll just have to find it because I've got two recordings going at the same time, and if I don't synchronize them, then they're not going to match up. Okay, here we go. The barometer. The barometer was developed by see if I can spell his name right. Evangelista Torricelli. And all he did was he took a glass tube, and they were very good in those days at making glass tubes of any length and any diameter for that matter. Constant diameter. So he just took one of those tubes and he sealed off one end of it. Okay? So he has this tube sealed at one end, and he filled it with mercury. He needed a liquid. But he needed a liquid that was very dense. If he tried to use water and create this device, his tube would have had to been at least 33 feet long. But with mercury being 13.5 times denser than water, he could use a shorter tube. So he filled it with mercury, put his hand over it, and inverted it and submerged it in a container of mercury. Okay? So now this is mercury, and this is mercury. So when he took his hand off, and they didn't know about mercury poisoning back then, when he took his hand off, the mercury level dropped. It went down to like here somewhere. And he noticed that if he went down to the ocean, this rose up. And if he went through his barometer in the back of an ox cart and went up the mountain, it decreased. So he equated that to a change in air pressure. He said that the pressure of the air above is pushing on this liquid, and that force is being translated into here, and it can hold that column of mercury up at sea level, on average 760 millimeters. They also noticed that if you just sit that barometer on your desk and just watch it over time, they noticed that when the weather was starting to come through and get bad, like rainy weather coming through, the level of mercury would drop. And when it cleared up, the level of mercury would rise again. So they associated that low pressure with bad weather and high pressure with good weather, and we still do that today. All right, so let's go back. Now we have 760 millimeters of mercury at sea level on average is also equal to 1 atmosphere pressure. Okay, so now we have an equality, which means what in terms of dimensional analysis? We have a conversion factor. Every time you have an equality, you can make a conversion factor out of it. Just ratio these two together. If you want to change some millimeters of mercury, and you want to change it to atmospheres, then you need millimeters of mercury on the bottom and atmospheres on top. So 1 here and 760 here. And there you have your atmospheres. We also can go back to this arrangement and say the pressure here, say we have pounds of force per square inch. That's also PSI. So PSI, in terms of these two values, is 14.7. Right? So now, how many conversion factors can we get out of that? We can get 1, 2, 3, right, conversion factors. And if we flip them, we can make 3 more. So you can actually get 6 conversion factors out of that, depending on where you start and where you want to end up. The SI units for pressure then would be, well, actually force in SI units is a Newton. So that's not quite right. The SI units for pressure is not kilograms per square meter. It's newtons per square meter. And that value, 1 Newton per square meter, is equal to a Pascal. 1 Pascal. We're not gonna dig into that too much, because it's not appropriate for this course. Okay, so I talked about that one already. 4 variables involved in the gas laws: pressure, volume, temperature, and moles. All right, for the first gas law, and we're going to take these in roughly chronological order. Robert Boyle was an Englishman, and the progression of these gas laws is dependent upon technology. Right? So they knew about temperature, they just didn't have a good way to measure it, right, for quantitative analysis. And Boyle was actually the first what we would call a quantitative scientist. His experiments had numbers associated with them. We knew about temperature, we just couldn't measure it very well. There are various attempts to do that at this point, but they weren't successful. One of them I used to have on my shelf. You've seen those tall cylinders with a liquid in them, and they got little balls with numbers hanging underneath them. No, you haven't seen those? That's an, what is that? Newton's thermometer. It's based on the Archimedes buoyancy principle. Well, anyway, so Boyle was stuck with measuring pressure versus volume. So he said pressure, and he said, what would happen if I changed the pressure? What effect would it have on the volume? And he found that if he took the value for pressure times the value for volume, he always got the same constant number for a given experiment. And he had to make sure that the gas was confined, so you couldn't put any more in, you couldn't take any out. That's fixed the number of moles, right? And the experiment occurred over such a short period of time, the temperature didn't change either. So this was Boyle's law. Pressure times volume is a constant. That's not very useful. What's more useful is if you look at it this way. Say during the experiment we say we take that pressure and that volume together and they give us a value. And then further down the line we change the pressure and we get a different volume. Right? It's also equal to K. Right? So what's that law in math? If A equals B and B equals C, then A equals C. I'm sorry?
that?
No, the Pythagorean theorem has to do with triangles. No, that's like, I think it's the cumulative law. If A equals B and B equals C, then A equals C. Anyway, so in that case, if these are both expressions equal to that value, then they're equal to each other. That's why P1 times V1 equals P2 times V2. And I call that, when you're solving problems, I call that a before and after. And we'll solve a few problems and it'll become more evident then. Now, what we do know is that what happens if this has got to be constant? What happens if we increase the pressure? What happens to the volume? If we make this one bigger, that one has to get smaller in order to keep that one constant, right? So, when you have two variables that are products equal to a constant, that gives you an inverse proportion. Okay? And let's see, are we going to graph it? No, we didn't. Okay, here's what it looks like when Boyle graphed his data. Oh, we've already done this too, right? In our graphing, right? So, who's controlling the pressure? Or is it the volume? Did Boyle change the pressure or the volume? He changed the pressure. So that goes on the x-axis. And this is the response. Now, the apparatus he used was actually a long tube that they heated and bent into a J. And he just put mercury into it. And the mercury pooled up on the bottom, and as he added more, and once it touched the inner curve, the gas in this part of the tube was sealed off. You couldn't add any more. So, as he kept adding it, he noticed that he'd get up, maybe put that much mercury in it, he'd only get that height on the other side. So he reasoned that the gas in here was pushing back. And if we plot the data at low pressure, you would have high volume. Right? And it would just keep going down and down and down and down. Right? And a best fit curve would be something like this. In math class, we call that a hyperbola. And actually, the formula for a hyperbola is something different than this, but it still gives you that same graph. And if we drew the rest of it, in math class, there would be another mirror image over here. Now, another characteristic of the hyperbola comes from this relationship. Can either one of these ever drop to zero? The answer is no. If they go to zero, then you don't have a value here anymore. So that's why you can never touch this axis with your curve. You can never touch that axis with your curve. It just goes on for infinity. Okay, and of course, when we did our graphing exercise, we learned how to create a straight line out of this. Remember that? You just take the inverse of your volumes and plot them against pressure, and you get a straight line. Okay, that's Boyle's law. So if we increase the pressure, if we double the pressure, then we're going to cut the volume in half. If we quadruple the pressure, we're going to cut the volume by a fourth. So if we go from 100 to 400 millimeters of mercury, the volume is going to go from 8 to 2. And we can use any units of measure we want in this equation. We could use pounds and cubic feet if we wanted to. All right, so the Boyle's law would look like that one right there. That's the practical application of Boyle's law. All right, how are we doing? 11:35. Okay, we're doing okay. All right, so a sample of helium gas, and by the way, it doesn't matter what gas it is, right? What's that poem, a rose is a rose is a rose? Well, in our case, a gas is a gas is a gas. Doesn't matter what it is, it will obey Boyle's law, as long as we have the high pressure, high temperature, and low pressure. So, a sample of helium gas occupies 12.4 liters at 23 degrees Celsius and 0.956 atmospheres. What volume will it occupy at 1.2 atmospheres, assuming that the temperature stays constant? Okay, so here's what I do. If I want to use that formula, let's see, let's put it over here. P2, V2. I set up a table. P1, V1, P2, V2. And here's where the before and after comes in. What are the conditions before? Volume 1 is 12.4 liters. What's the pressure at that volume? 0.956 atmospheres. Then the question is, what's the volume if we increase the pressure to 1.2 atmospheres? Now we put numbers where they're supposed to be. We can fit them into the equation and solve it. Let's see, did I solve it here or do I need to do it on the board? There it is. So that ensures that you're going to put these values in the right place. Because if you don't do that, you'll always get the wrong answer. So our volume went from 12.4 to 9.88 because we increased the pressure, so the volume had to decrease. All right? And all you had to do was solve for the unknown. Is that everything in the right place? 956 times 12.4 on this side. And this pressure is 1.2, and this is our unknown. So you just take this value, put in the denominator on this side, and crunch the numbers. All right, that's Boyle's law. After several decades, those who are working to standardize temperature measurement finally came up with some useful values, useful instrumentation. So then, once you can measure the temperature, then you can say what would happen if these two were our variables and these two were constant. And find out what the relationship between volume and temperature is. And Jacques Charles did that. I think he was, well, if I'm correct with his first name, he was French. Charles' law. Actually, I think Charles was given credit for the law, but he didn't publish the work. He communicated with other scientists through letters, and Gay-Lussac took that information and ran with it. And when he published his work, he gave Charles credit for this law. That's why it still has his name on it. Okay, so what Charles' law found out was that volume divided by temperature equals a constant. Okay, so what that means is, if this is constant, if volume goes up, what has to happen to temperature? It goes up too, right? So this is a if you have a quotient relationship, that means a direct proportion. As one goes up, the other one goes up. And I think we saw that in our graphing example too. What Charles could do with his, he changed the temperature and watched what happened to the volume. And any gas would give him a straight line. If this is degrees Celsius, and this is, say, liters, and these straight lines would be, they would be different for each of the gases. But they would usually intersect somewhere. And actually where they intersected was, according to Lord Kelvin, out here at 0 K, absolute zero. And this is minus 273 degrees C. All right, so we can set this up like we did the Boyle's law, before and after. That's a more useful version of Charles' law. Except Charles did his experiments this way with degrees Celsius, but he didn't extrapolate them. I mean, he always had a positive value. But if you want to extend the range into the negative temperatures for Celsius, you can't do it with this equation. Because once you get below zero, then your temperatures go negative. And that just blows the whole thing up. So we get around that by using an absolute scale. By converting our temperatures to Kelvin, now we always have positive values. So remember that whenever you're using these gas laws, this has to be in Kelvin. Just take Celsius and add 273 to it. And this shows the direct relationship. If you have 2 liters of gas at 100 K and you increase the temperature, if you double the temperature, you'll double the volume. If you double the volume again, you'll double the temperature, you'll double the volume again. So it's a direct relationship. All right. So let's take a problem example here. And again, we might as well set it up now. B1, T1, V2, T2. What's the before? Now, how do we know it's a before and after situation? Well, you've got 2 of each one, or the question includes one of them. 1.3 liters of air at 24.7 degrees. Degrees C. And we want to know what's the volume if we place the container in liquid nitrogen at minus 78.9 degrees. Wait a minute, place into a containing liquid nitrogen. We put a balloon, that's not right. No, it's not liquid nitrogen. That temperature is liquid carbon dioxide. Actually, it's dry ice. Right? Well, it could be liquid. That's liquid. The boiling point of liquid carbon dioxide is minus 78.5 degrees. Nitrogen would be minus 195 degrees. So that's an error. That's an error in the slide. And let me make a note. But if we change our thinking and say liquid carbon dioxide, right, instead of nitrogen, and use minus 78.5 degrees, minus 78.5 degrees Celsius, then we can calculate volume, right? Not yet. We have to convert that temperature to Kelvin. So how do you do that? Plus 273 plus 273. This one's fairly easy. It should be 297 like that. And this one would be 78.5. 5, 8 and 13 is 5, and 7 and 16 is 9. 195.5. Now we can put our values into the equation and solve it for the unknown. Oops. There it is. So, if we decrease the temperature of that balloon in liquid carbon dioxide, we decrease the volume from 1.3 liters down to 0.849 liters. Think you can solve these problems? Practice, practice. Okay, let's see. Oh, that's right, we left one out. So, this is not in your slide set, but I'm going to give it to you anyway. Alright, now we're going to hold temperature and pressure constant. And we're going to we're going to add more gas and see what it does to the volume. This is Avogadro's law. In this case, we find that when we add more gas to the container, if the pressure is constant, the temperature constant, the container expands. And it's a direct proportion. So V1 over N1 equals V2 over N2. Right, there we have a quotient, which means it's a direct proportion. Okay. I don't have time to go into more details there. We'll pick it up later if we have time. But what we're going to do now is say, all right, what if you've got a situation where all four of them are changing at the same time? What do you do with that? And that's more likely that you're going to find in nature. What you need is what's called the combined gas law. So if we start off with Boyle's law, like pressure times volume, pressure 1, volume 1, equals pressure 2, volume 2, and then we introduce Charles' law, temperature right, volume to temperature. Then we introduce Avogadro's law, volume and moles. Now we have a combined gas law. P1V1 over N1 T1 equals P2V2 over N2 T2. That's the combined law. Now, if any one of these is constant, then you can throw it out. Say if you got the same moles on either side, then you have that one. Or if you have the same moles and temperature on both sides, now you have Boyle's law. Okay, so that way you can solve more complicated problems. Now the authors of the book left out Avogadro's law. I stuck it in here. Okay. So if we're going to use the combined gas law, it's extremely important now that we set up a table and put the values in where they need to be. So if we have P1, V1, N1, T1, and P2, V2, N2, and T2. We're going at what temperature does 121 milliliters of CO2 at 27 degrees in 1 atmosphere occupy a volume of 293 mils and a pressure of 1.4. All right, so at what temperature? We're saying that's where we end up. So we're looking at this one is our unknown. We're starting with 121 milliliters at 27 degrees Celsius and 1.05 atmospheres. All right. Then we get a final volume of 293 milliliters and a pressure of 1.40 atmospheres. Now, it didn't say anything about the moles, did it? This gas is confined. We're not changing the number of moles. So we can throw that one out. And we don't even need to use it. So now we can either plug the values in and solve for the unknown here, or we can solve for the unknown and then plug the values in. It works both ways. Let's see how I did it here. I plug the values in and then solve for the unknown. But this has to be changed to Kelvin, which would be 300. Okay. Now what's the temperature going to come out here with the solution of the problem? It's going to be Kelvin, right? And if the question asks for Celsius, then you have to take this value and subtract 273. And that equals degree C. Okay? Now, those were all before and after situations. If you know where you came from and where you're headed, except for one factor that you have to calculate the answer, then this works really well. But suppose you have a certain state that's defined and you don't know where you came from. Right? You're only given single values for 3 of those 4 variables, and you got to solve for the last one. We have what's called the, if we have P1, V1 over N1, T1, and that's equal to a constant, right? That's our combined gas law. Then if we know what the constant is, and we know what 3 of these are, we can solve for the other one. But when we use this ideal gas equation, we need to be extremely careful about the units of measure. And how do we know which units of measure are appropriate for each one of these variables? Go to the constant. In this case, the constant is given a special letter, R, and for our purposes now, we're going to be liters in volume, atmospheres in pressure, moles, and K for temperature. So each one of these values has to be in liters, atmospheres, volume, moles, and K. If we had any other values in here, then these would have to be converted to reflect that. Otherwise, the equation won't work. And if we do it this way, for gases, this is 0.08206. They rounded off to 821. I guess that's okay. It'll get you close enough to answer questions on the test. Okay. Now, one other thing. If the problem states, anywhere in the problem, it states STP, That's not a gasoline additive. That's standard temperature and pressure. So standard temperature and pressure for gases, as long as we're working with these gas laws, standard temperature is 0 degrees C and pressure is 1 atmosphere. Okay? All right. So here's an example. Say we have an automobile tire at 23 degrees C, an internal volume of 25 liters, and you fill it with air to a total pressure of 2.18 atmospheres, or 32 pounds per square inch. What are the number of moles of air in the tire? So you set up your table, pressure, volume, moles, temperature, and you plug in the values for each one. Let's see, 2.18 atmospheres. Okay, so that's compatible. Volume, 25 liters. That one's compatible. Moles is our unknown. And temperature is 23 degrees C. That's not compatible. It needs to be K. So we add 273 to it. And that's 296K. Now that we have those values, we can plug them in with this constant and solve for moles. And that's what I've done here. So when we solve that equation, we find that the number of moles is 2.24 in that tire at 32 pounds per square inch and 25 liters volume. Okay. This one is slightly more involved. What's the pressure in a 304-liter tank? Pressure. Question. Volume is 304 liters. 304 liters. That's good. Containing 5.670 kilograms of helium. So mass equals 5.670 kilograms of helium at 25 degrees. So temperature is 25 degrees C. We'll go ahead and add 273 to it, and that's 298K. What's missing? If we're going to use the ideal gas equation, what's missing? Moles. Can we find the moles of gas? Yeah. Because we have the mass of gas, and we have the identity of the gas right here. So, what's the magic number? Molar mass. Right? But molar mass is in grams per mole. And this is kilograms. So how do you deal with that? Right. 5.670 kilograms. If we take the kilo, what does it mean? It means 1,000 times. Times 10 to the third grams. So I just took this and converted it into a number, and there it is. So that's our grams of helium. We want to convert it to moles. So how much does helium weigh? Mass of helium. Let's see. 4.00, rounded off. Okay, so that'll give us moles. And then we can plug those into the equation and solve for pressure. And the pressure should be 114 atmospheres. That's a lot of pressure. So my guess is, at that pressure, we're starting to deviate from ideal. Right? For our purposes, it's close enough. But if you were an engineer working on this problem, that pressure would be bordering on a problem for your calculations. because the gas is no longer acting or behaving ideally. All right, one more gas law. Dalton's law of partial pressures. And this is the same, this is John Dalton, who gave us the atomic theory. He also worked with gases, as did most of the scientists in his day. And all it says is, if you measure the pressure of a mixture of gases, right? If you have a mixture of gases, what are they also called? Well, they're always homogeneous, so that makes them a solution, right? Solution of gases. That pressure that you measure is equal to, the sum of the pressures of each of the individual gases. It doesn't matter how many you have. Right? So what we're trying to show here is the red gas is a value of 1, the blue gas is a value of 3, and the green gas is a value of 2. If you put them all together under the same identical conditions, then you're going to get a pressure of 6. It's just additive. Okay, so a gas mixture containing oxygen, helium, and nitrogen. So this would be oxygen, this would be helium, and this would be nitrogen. Okay, has a total pressure of 780 millimeters. 780 millimeters of mercury. Okay, what's the partial pressure of oxygen? Right, that's the question. If helium and nitrogen are 86 and 124. So helium is 86 millimeters of mercury and 124 for nitrogen. That should be simple. Just take 780 and subtract 86 and 124 from it. And you get 570 millimeters of mercury. That's the partial pressure of oxygen in that container. Okay. Let's solve this problem. And I'll give you a hint. It's going to require 2 different laws combined. If we have this vessel connected by a valve, and on the right hand side we have 3 atmospheres and 3 liters. 3 atmospheres and 3 liters volume. And on this side we have a bigger one, 9 liters at 2 atmospheres. Okay? The question is, what's the pressure if this is helium gas and the temperature stays the same throughout the experiment at 45 degrees C, right? Temperature doesn't change. After the valve is open, what is the pressure of the total pressure of the combination? Well, let's look at this intuitively first. Lost somebody? Yeah. Bye-bye. If we open this valve, which way is the helium going to go?
Smaller.
2 atmospheres, 3 atmospheres. The other way, right? Small end is going to deliver some gas into the big end. What should we expect the pressure to be? Just a range. Is it going to be higher than 3? No, because we lost some of that pressure. Is it going to be 2 on this side? No, it's going to be greater. So the pressure should be between 2 and 3 atmospheres at the end. Okay, here's how you solve this problem. We know that the partial pressure due to this one be, after you open the valve, you're going to have the partial pressure of, let's say, I don't know, let's say 2. Partial pressure of 2 plus the partial pressure of 3 liters versus 2 liters, right, let's do that, is equal to some value. And that's the one that we're looking for. So we got to find out what each one of these is, right? Okay. So here's the way you do it. You use a thought problem. Assume that that one is a vacuum. And if we open that valve, it's going to rush into that vacuum, equalize itself, and give us a new pressure. Okay? We're going to use Boyle's law, before and after. So before, pressure here and volume here. What's the volume 2 going to be? It's going to be 9 plus 3, or 12 liters. So the pressure 2 now is our unknown. Okay? So now all we have to do is say, all right, PV divided by V2, V1 P1 divided by V2. Remember, if we have this one, P1 V1 equals P2 V2. We're solving for this one, that V2 comes over here. Right, so that V2 is there. So all we have to do now is say 2 times 9 divided by 12. That would be the partial pressure of the helium from this side. Right? If we're making that a vacuum, then its contribution is going to be spread throughout both of them. Let's see. It's 18 divided by 12 is 1.5. 1.5 atmospheres equals the pressure of wait a minute, that's atmospheres. Atmospheres. Of the 2 atmosphere side is 1.5. Okay? Now we need to do the same thing with this one. So now this one's going to be V1 here and P1 here. And V2 is the same. Right? It's expanding into the same volume. So now we need 3 times 3 divided by 12. So 9 divided by 12 is 0.75 atmospheres. And this is P 2 atmospheres, and this is P 3 atmospheres. Yes, 3 atmospheres. Okay, 0.75. Add them together. 2.25. That's the total pressure after you open the valve. So we use Boyle's law first, and then we combine them using Dalton's law of partial pressures. Does that spin your head around? You have to imagine. Imagine a vacuum, solve that one. Imagine a vacuum, solve that one. That gives you pressure due to this side, and then pressure due to this side, and the total is the combination. But it showed up where we expected it to be, right? Between 2 and 3. That's what we expected. So that's sort of confirmation. And this is probably working out the problem, like I mentioned earlier. Okay, we don't need to pause for the next class because we got the lab time to use it up. We can finish this whole thing. Finish chapter 7 today. Let me see. How we set up. since we got the time, I think we ought to get this one out of the way. Because we've got chemical change coming up as a lab. That way we can talk about it first and then do the lab. And then come back on the 31st of October and get Chapter 8 out of the way. Maybe what we can do is talk about chemical change and Boyle's Law next week so that we be prepped for Boyle's Law the following week. And that way we can get Chapter 8 out of the way and go straight into Boyle's Law Lab. Boyle's Law Lab is short and fun. Anybody come up with 2-liter pop bottles? No? That's okay. I drank 6 2-liter pop bottles in the last couple of weeks, and now I've got plenty of bottles. I probably drove my triglycerides through the roof. But they'll come down because I'm drinking water now. Okay. So let's look at, those are the gas laws. Now let's look at changes of state. We've already introduced some of this already with our discussion of kinetic energy versus potential energy. A change of state simply means that this physical property that we described as gas, liquid, or solid actually is a physical change. So we've taken that potential for being gas, liquid, or solid, and we're talking about the change now, the actual change from one state to the other. But the substances that are part of that change do not change their identity. Right? If it's water changing, it's still water, just a different physical state. Identity is the key. So, the way I put these together is I say, okay, here's our gas here. Here's our liquid over here. So you put it over there. And here's our solid over here. And it's the same substance. Right? It's just undergoing changes of state. And we have words for these. Right? The first one, freezing. If we go from a liquid to a solid, that's freezing. Okay? If we go from a gas to a liquid, that's condensation. Okay? If we go from a gas to a solid, that's deposition. Okay? If we go from a solid to a liquid, that's melting. Next one, if we, evaporation is liquid to a gas. Okay, so this is evaporation. And if we go from a solid to a gas, that's sublimation. Okay? Those are the 6 possible state transitions and the words that are associated with them. I like my drawing better than theirs. Except that this also includes what is the heat movement. I mean, in order to go from a liquid to a gas, we have to increase the kinetic energy of the molecules. So we're adding energy to it. We're adding temperature, heat. So this is And by the way, I might as well throw this in. When we talk about the sign on heat, movement, it's in terms of the system. Right? Here's your system. And everything else is surroundings. Right? So, if we're getting a liquid to evaporate, the liquid here, we're going to change it into a gas. Now, we're supplying heat to that to do it, right? So the heat comes from the surroundings. And the heat is introduced to the system, and we use a little Q for the heat. We introduce heat to the system in order to make that change. So the sign is relative to the system. We have increased the heat content of the system. That means Q is positive. So evaporation is heat absorbed. Okay? If we go the other direction, we go from gas to liquid, condensation, Q is negative because heat has to leave the system to go backwards. Okay? And with that in mind, we can do that for each of the others. If we're going to melt something from solid to liquid, we have to add heat to it. Q is positive. Go the other direction, Q is negative. Okay? If we go from solid to gas, we have to add heat. And if we go from gas to solid, we're going to give up heat. Okay? Now, we got special terms for these. Let's see. This is a negative and there's a positive, so I'm going to use these. If the heat is leaving the system and we give it a negative, this is called exothermic. Think of heat exiting the system. It leaves, exothermic. If we have to add, that's endo, going into, endothermic. So, endothermic processes absorb heat. Melting, sublimation, evaporation, those are all endothermic processes. Whereas freezing, condensation, and deposition, those are all exothermic because as they transition to liquid or to solid here, they have to give up energy to do that. Give up their kinetic energy in order to either become a liquid or a solid. All right. Let's see. Let's do this in the form of questions. Evaporation. What's happening on the molecular level? What's the kinetics of this process? The change is evaporation. Right? We're going from a liquid to gas. Molecules are getting farther apart. We have to add energy to do it. And why do we have to do that? Because of the cohesive forces, the potential energy, the cohesive forces holding those molecules together must be overcome in order to spread them apart into a gas. And it takes a lot of energy to do that. Now, that's in general terms, in equilibrium terms. We know we start with a liquid, we end with a gas. But what happens in between? How fast can it happen? That's another discussion altogether. The rate of evaporation happens quicker if the temperature difference is larger. And you know that from practical about put soup on the stove, right? You want to heat it up slow, just turn it on low, right? You want to heat it up fast, turn it up to high, but don't walk away from it because it'll boil over. So it happens quicker if we increase the rate of input of energy. So As something evaporates, say you have it's a nice bright sunny day and you just come out of the pool and you've got water all over your body. Right? It feels like you're cooling down, doesn't it? It should, right? Because as the water evaporates, it has to gain energy from somewhere to go from a liquid to a gas, because it's endothermic. So where does it get that energy? From your body. Your body is the surroundings. It supplies energy to evaporate that water, so it should feel cooler. All right. Okay, so we're taking this evaporation process and the condensation process, and we're going to expand on that. We know it happens faster with higher temperatures. More heat over a period of time goes in. But we can also look at it in another way. Say we have a closed container. Get rid of this one. Say we have a closed container. Well, actually, say we have an open container first. And we have a liquid in the bottom. Right? At a given temperature, say 25 degrees Celsius. What's going to happen? Well, depending on the liquid, it's going to evaporate either slower or faster. But eventually, it'll continue to evaporate and just all be gone. Right? Suppose, though, we put a cork in it. Now it can't leave. What's it going to do? Well, it's going to become a gas. At first, it only goes one direction. We're putting these molecules into the vapor phase. But eventually, you get enough of these up here, they start going back. And when these processes happen at exactly the same rate, that's when you have equilibrium. You'll notice in the beginning that the volume drops. Right? Yeah. It drops. But eventually, it stops. It doesn't drop anymore. So these processes of evaporation and condensation happening at exactly the same time is a physical equilibrium. Right? Equal means equal rates. And when it does that, depending on the liquid, you get a measurable pressure in that space. Right? And that's known as the vapor pressure of that liquid at a given temperature. If it's water, it'll have a certain pressure. If you put something that's more volatile, like turpentine, it'll produce a higher pressure. If you put ether, right, it'll produce a massive pressure in that. So you want to be sure you have a strong container. And it all has to do with the attractive forces in the liquid. Right? If the attractive forces are very high, it takes more energy to get them out. So at any given temperature, for different liquids, it depends on what's attracting them. So water has a very high attractive force. It's going to have a low vapor pressure. If you go to ether, the attractive forces are very low. So at any given temperature, it's going to put a lot of them into the vapor phase for that amount of heat. That's why its pressure is higher. That's known as a physical equilibrium. The forward and the reverse processes happen at exactly the same rate. Now we could talk about chemical equilibrium, but I think that's beyond the scope of this course. If it does crop up, it won't be exhaustive. Okay, like I said, that's the vapor pressure. And the stronger the attractive force, the lower the vapor pressure for any given temperature. There's dimethyl ether, right? I think what they used to use in the operating theater was diethyl ether. I'm pretty sure it's the ethyl ether. So instead of CH3 on one side, it has CH2, CH3 group on that side, and the same on the other side. Anytime you have an oxygen with connected to two other things on the other side, it's an ether. Okay. So, a liquid in a closed container evaporates for a short time, then condenses as the number of vapor molecules increase. This process is known as physical equilibrium. And again, the identity didn't change. It's just in a different phase. Right? This is a physical change producing vapor pressure. Now, this happens at any temperature. As long as there's liquid, it's going to be generating vapor. If the temperature increases, it'll make more vapor. But when we produce vapor from within the liquid at a given temperature and atmospheric pressure, that's called boiling. So it's vaporization, but it's a special case. This is a form of evaporation where the liquid state goes to the vapor state within the body of the liquid. Right? So when you put water on the stove to boil, you're going to make pasta maybe. What does it do first as you heat it up? You start to see little tiny bubbles, don't you? Down, usually forming on the metal or the whatever the surface is. That's not water vapor. Those are dissolved gases coming out of solution. Gases in liquids are more soluble at lower temperatures and less soluble at higher temperatures. So when you first start heating it, you get the gas, you degas the solution or the water. And then eventually you get hot enough to where you can produce the vapor bubbles. That's why when I had all those 2-liter pop bottles I brought them home from the store, I immediately stuck them in the refrigerator. I wanted them to get cold because they've got carbon dioxide dissolved in them. That's the fizzy part. And if I open the cap at room temperature, it's going to go whoosh and lose a lot of that gas because it's high temperature. Lower the temperature in my refrigerator, pull it out, first time you crack it, it goes shh. Then all the fizz is in your drink. Okay, there's boiling. Now, the boiling point will be different for different atmospheric pressures because there's a say an opposing force. If the pressure is 1 atmosphere, it's a certain force holding back vaporization of the molecules from the surface. If we decrease that pressure, then more of them can come off the surface at that same temperature, right? And they can actually start boiling at a lower temperature if we decrease the head pressure. So let's see, at 1 atmosphere pressure, say sea level, pure water will boil at 100 degrees Celsius. Around here, we're at, well, in Beckley it's a half a mile high. Pressure is decreased. So water will boil at, say, 95 or 94 degrees Celsius. If you go to the top of Mount Everest, it'll boil in the neighborhood of maybe 80 to 82 or 3 degrees Celsius. So, if you go to Denver and try to boil a 3-minute egg, you better add another minute because the water's not as hot as it would be at sea level. So, long story short, boiling point changes with elevation. Boiling point decreases with elevation. Now, when we say normal boiling point, we're specifying the pressure over the liquid to be 1 atmosphere. So that value is calibrated for 1 atmosphere head pressure. and that temperature will be the boiling point, normal boiling point. All other boiling points are dependent upon temperature. All right. Oh, there it is. I was wrong. Mount Everest is 70 degrees. So, but once you get up to the top, you're not too concerned with boiling a 3-minute egg. You're more concerned with getting down alive. Like they had just recently, they had that freak snowstorm that came in and killed a bunch of people at base camp at Mount Everest. Okay. So, and if you go down below sea level, the boiling point goes up. So that's why pressure cookers work the way they do. Right? You seal that vessel off, and then you put this thing on top that provides a certain amount of head pressure. So as you heat the water up, the pressure builds up, and you generate, I think those rings have, the little ring in there without anything attached to it is 5 pounds per square inch. Put in one ring is 10 pounds, and 3 rings is 15 pounds. So you put the whole thing on top, that's 15 pounds per square inch, and the boiling point of water goes way up. And if you're canning stuff, let's see, what is it? 20 minutes at 15 psi will kill anything, any bacteria. I don't know about viruses. I think they're a little hardier. Okay. So there's the boiling point, the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure exerted on the liquid. So, this is a trick question. What's the vapor pressure of water at 100 degrees C if boiling? If it's boiling at 100, you know the pressure has to be 1 atmosphere. Okay. Now let's talk about the forces between molecules and within molecules. Intramolecular forces are the forces holding the molecule together, the bonds. Intermolecular forces are the forces that independent molecules feel when they approach one another. Yeah, within molecules is intra, inter is between molecules. Now, which one's bigger in terms of strength of the interaction? The ones within the molecule. Think of it this way. If the intramolecular forces were weaker than the intermolecular forces, the intermolecular forces would rip the molecule apart. Right? It's just that simple. So the forces holding the molecule together must exceed the size of the intermolecular forces between molecules, otherwise they break apart. Now that does happen, right? And you get a chemical reaction when that happens. Okay. We can classify these intermolecular forces between molecules as either well, actually, let's go back to the polarity of molecules. If a molecule is polar, it has what's called a dipole moment. So the molecule would have something, say, expressed like this. And we saw that with the water molecule. So this would be some molecule. If you got another molecule, and this would be the positive end, this would be the negative end. If this comes close to another molecule that also has a dipole moment, and they happen to be oriented this way, so this is the positive end, this is the negative end, you get an attraction between those differences in charge. That's a dipole-dipole interaction. The dipole interacting with the dipole. Okay? Now, if, and this is a special case of dipoles, if you have an electronegative atom that's either oxygen, nitrogen, or fluorine attached to a hydrogen, and this can be anything else, then you get a particularly strong dipole. And then the interaction can be between this part of the molecule and another molecule, where, say, the hydrogen is here and the oxygen is here, like that, and then you get that. When that happens, when you have a hydrogen attached to any one of these, you have the potential for hydrogen bonding. And hydrogen bonding is a special category of dipole-dipole, which is the strongest dipole-dipole interaction that we know of. Okay? So hydrogen bonds are a subset of dipole-dipoles, but it's a strong subset. Now, what else can happen? Well, if we have, say, a liquid with this dipole, and we put something that's soluble, right, and makes ions, say an ionic compound. It makes, say, sodium chloride. So we have our sodium ions and we have our chloride ions. We can get an interaction between the negative and the positive. That's a dipole-ion interaction. So that's what happens when you put salt in water. Now, that's when you have a permanent dipole for any of the molecules. If you have a nonpolar substance, you still have the potential for interaction, but it requires a temporary distribution of electric charge. So let's say we have, pick a good example. Okay, let's take nitrogen. There's our nitrogen molecule. Definitely nonpolar. Because we've got two of the same atoms, they're pulling equally on electrons, that's a nonpolar molecule. So, if we decrease the temperature to minus 195 degrees Celsius, what are we doing in terms of kinetic versus potential energy? We're decreasing the kinetic energy significantly, aren't we? That disruptive force is being decreased so much that now the attractive forces, the cohesive forces, have a chance to take over. So if we cool it down that far, then you go from a gas to a liquid. How does that happen? It's a nonpolar molecule. How do we get attractive forces out of that? Temporary charge. So what happens is, electrons, think of electrons as always in motion. They will not sit still. On an atom, on a molecule, they're always in motion. So there's always a potential for an instant to have a slight negative side and a slight positive side on that molecule. And it doesn't last forever. It just lasts long enough so that it can influence its neighbor. If this one's negative, it's going to repel electrons from this one, making it slightly positive, and this side attracts them, making this slightly negative. And for that instant, you get an attraction. Now this is a very, very, very weak attraction, very weak force. But even in polar molecules, it's there. It's just that these forces are so much stronger, this London dispersion force is insignificant. It's only significant when there's no opportunity for polar interactions to swamp it. And this is an example. So those are your intermolecular forces in a nutshell. And I've already explained this. Unusually strong hydrogen bonding. Okay, fluorine, oxygen, nitrogen, I got that right. Now, what we're trying to explain here is why the hydrogen bond is so much stronger than just any old ordinary polar bonds. First of all is the electronegativity of the element attached to hydrogen. Notice where we are in that periodic table. We're at the upper right-hand corner. That's where the high electronegativities are located. Fluorine, nitrogen, oxygen. And then couple that with covalently bound to a hydrogen atom. When you bound a hydrogen atom to anything, what do you got? You're bound to a proton, right? It's tiny, right? So what that means is with a very small hydrogen nucleus with one proton, you can get these things close together. Say here. You can get extremely close here. And electrostatic attraction increases as distance decreases. Actually, it's by the square. So when you get that close, the combination of electronegativity difference and proximity increases the forces dramatically due to that small size of the hydrogen nucleus. This is water. Okay. So what we notice is when we measure the vapor pressure of liquids that have hydrogen bonding associated with them, they have very low vapor pressure because the liquid has very strong attraction for its neighbors, and it takes a lot of energy to break that intermolecular attraction to get them away. So things like water would have a very low vapor pressure. What are some other possible hydrogen bonding? How about ethanol? There's your hydrogen bonding for ethanol. Right. Now it's not as strong a bond as water because you got this big mass out here. But ethanol, that's the drinking kind, has a, let's see, water has a boiling point of 100 degrees at 1 atmosphere. Ethanol is about 78 degrees, so it's relatively high. Okay, so what we're trying to show with this slide is the nature of the hydrogen bond within hydrides of a group of elements. So if you look at the periodic table and you see oxygen, right? When you form a bond there with oxygen and hydrogen, you have the potential for a hydrogen bond. But if you go down to its neighbor, sulfur, right, that potential goes away because the sulfur electronegativity is too small, plus the sulfur atom is huge by comparison. And it gets even worse for selenium and tellurium. So the boiling point decreases as you decrease the strength of that attraction. Now, if we follow the trend from tellurium through selenium through sulfur hydrides, and we followed that trend on down to water, water should boil at about, minus 75 degrees Celsius. But it doesn't, right? Because of the hydrogen bonding. London dispersion forces, I described them earlier. And they are temporary. They occur for all molecules and all atoms. The London dispersion forces are stronger for large atoms and large molecules. So when you look at a series, the homologous series of hydrocarbons, well, I'll tell you what, it might be easier to study if we use noble gases. Let's just use atoms. They have London dispersion forces associated with it. So if we go from helium to neon to argon to krypton to xenon, what's happening? These atoms are getting bigger and bigger. They're getting huge. Xenon atom is a monster. The more volume you have for the electrons to move in, the more likely you are to unequally distribute them temporarily to get positive side and negative side. So what we find is that the boiling point from there like that increases. We know it can't be polar, right, because there's only one atom. So the London dispersion forces are active, and they explain why the boiling point increases as you increase the size of the atom. Because the London dispersion forces then become more significant, stronger. Now you can do that with molecules too. I was going to put the hydrocarbon series up there, but that's okay. If you become an organic chemist, you'll learn all about it. If you don't, then it won't matter. I will say that there's a difference between, let's see, methane, right, which is a gas at room temperature, propane, which we can make into a liquid, which is a bigger molecule. We use it in our grills. You can go to gasoline, which is a liquid at room temperature. It's octane. Right? Or you can go to diesel oil, which is thicker. It's a larger molecule. Or you can go to asphalt, right, which is it's only liquid when you heat it up. And then mix it with, what do they call it, aggregate, and pave your roads with it. So the molecules are getting bigger and bigger and bigger. The forces attracting them get larger and larger. Okay, oh, there's the values. So you can see as the masses increase there from helium to, well, they've got radon in there too. I didn't put radon in there because it's radioactive, so you don't want to mess with it anyway. And you see the boiling point goes up. Right? Helium is minus 269, goes all the way up to minus 107 for xenon. And the explanation is London dispersion forces. All right. Which are stronger, intramolecular or intermolecular? Intra. Yep. All right. Which has the stronger intermolecular forces? Nitrogen or water? Nitrogen is a nonpolar molecule. Water is a polar molecule with hydrogen bonding. So the water would have the stronger intermolecular forces. And you can see that in the boiling points. Water has a massively higher. It's almost 300 degrees Kelvin higher boiling point than nitrogen. Here's another. I erased it. Ethanol is the one on top. Right? It has hydrogen bonding. We take the same exact molecular formula, C2H6O, and we rearrange the molecules to make dimethyl ether. And notice the difference in boiling points. The intermolecular forces for ethers are much, much lower because now we don't have hydrogen bonding available. Which gas would behave more ideally at the same conditions of pressure and temperature? When we talk about ideal behavior, What we want to do is, whenever these gas molecules encounter one another, we minimize attraction-repulsion forces. That contributes to ideal behavior. So which one of these would have the stronger intermolecular forces? The carbon monoxide. So the more ideal behavior would be nitrogen gas. No intermolecular interactions to speak of. And there's why. Oh, we're almost done. Concept questions. That's the clue that we're toward the end. Okay. So let me clear the board. And yeah, we got time to cover these guys. All right. To hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. When you retrieve them, you're disappointed to find the balloons deflated. Well, that assumes we've got some ice in that freezer. So, temperature change, volume decreases. As they warm up to room temperature, they return to their original size. What gas law is demonstrated in this scenario? Temperature volume. Whose gas law is that? Charles. Yes. Yeah, Charlie's law. What happens to the kinetic energy of the helium during the warming process? Kinetic energy increases. Yeah, kinetic energy increases with temperature. So, D would be the correct answer. How about this one? A gas-water displacement experiment is set up and it's determined that 0.812 grams of gas displaces 350 milliliters of water. The atmospheric pressure is 750 millimeters of mercury. Temperature of the water is 20 degrees and the partial pressure of the water is 18 millimeters of mercury. What's the molar mass of the gas using the ideal gas law? Okay. Picture time. Draw a picture. This is a gas-water displacement experiment. This is what it looks like. Right over here. So we have this container of water. Right? And we have a measuring device in here, say a graduated cylinder, which is inverted. Let's do like this. And there's the base. And it's got markings on it for volume. Okay? Now, when we set it up, we fill it with water and turn it over. So there's water from here down to here. Now, of course, it's going to drop a little bit when you take your hand off of it, just like the barometer did. We're producing a gas over here in this experiment, and we're sending it over here. Right? So as the gas is produced, we get bubbles. Right? And they displace some of the water. Now actually, once we've got finished the reaction and we've captured the gas up here, in order to not introduce any error, we have to move this cylinder down until that level is equal to this level. Because only then is the pressure inside equal to the pressure outside. Okay? Okay. So, how do we determine the molar mass of the gas? Well, molar mass, or molecular weight, is mass per mole. So we need two values to do this. We need the mass of the gas and we need the number of moles. So the mass of the gas is given, 0.812 grams. 0.812 0.12 grams. What we need to do is find the moles. Okay, so can we find the moles? We know what's the pressure, 750 millimeters of mercury. That's equal to pressure. Okay, volume. Is that the volume? Yeah, 350 milliliters of water are displaced. Okay. Let's see. Temperature of the water is 20 degrees. So 20 degrees is going to be the temperature of the gas and the water. Right? So temperature equals 20 degrees C. Why do we know that this is 20 degrees? Because the gas bubbled through the water and equilibrated its temperature. Okay, and the partial pressure of the water is 18 millimeters of mercury. Pressure of water is 18 millimeters of mercury. All right, here's the problem. When you bubble gas through water, what's it going to do? It's going to pick up water vapor. So up here, this 350 milliliters is a volume of water vapor plus our gas. Okay? So the pressure that we need to know is how much of that pressure is due to that gas. Well, we know the pressure inside there is 750 millimeters of mercury because the pressure outside is that. So what's the pressure of this gas? It's 750 minus 18. 742, right? Or is it 30? 32. Yeah, 732 millimeters of mercury. Okay? So, we got the pressure of the gas, we got the temperature of the gas, we got the volume of the gas. Right? These two gases, water vapor and our gas, occupy that same volume. So the volume didn't change. Right? So we have volume here. So if we use this expression, our ideal gas law, am I running out of time? Or are you running out of time? Oh, okay. We want to find out moles. So N equals PV over RT. What's the pressure? Well, what's the value of R? 0.8206 liter atmospheres per mole K. So we need pressure in atmospheres. This needs to be divided by 760 to give us atmospheres. 732 divided by 760 is 0.9632 atmospheres. So we got that term, 0.9632 atmospheres. How about volume? It needs to be in liters, doesn't it? So, how many liters is 350 milliliters? You do that one in your head? Move the decimal 3 to the left. 0.350 liters. Down here we have R, 0.08206 liter atmospheres per mole K. And temperature is what? 20 plus 273 equals 293 K. So this is 293 K. So there times 0.35 divided by 0.08206 and divided by 293. So I get 1.402 times 10 to the minus 2 moles. So if we put that up here, 1.402 times 10 to the minus 2 moles, we should be able to calculate 0.812. Rounded off 58 grams per mole. Oh, I worked it all out, didn't I? Okay, there it is. Black and white and blue and red and green. Okay, there's number of moles, and oops, and there's the calculation of moles. So how did we solve that problem? What's the question? We want to know the molar mass of the gas, right? That's molar mass. So we went looking for the information. Do we have the mass? Yeah, we have the mass, so we put that in there. Then we had to figure out how to get the moles, right? When we're dealing with a gas, then we introduced first Dalton's law of partial pressures, because we've got a mixture of gases, water vapor and the gas we want. So we separated those first. Then we used the information we had to find the number of moles. Then we plugged in and we're off to the races. Okay? So this is what's known as a multi-step problem. But you got to ask the right question and see what you're given and then what you need. And that's it.